So for this first one, the square root of 50, we know we're going to end up with 5 square root of 2. But where does that 5 come from? Yes?
Wasn't it a multiple of 50 as in, like, it would have been 25?
Right. Very good. So the first thing you want to do, and I heard some people saying that when they were working in their groups, is that you want to find a perfect square that you could say divides evenly, or you could say is a factor. All right, and then in this case, we're looking for a factor of 50. Obviously, that changes from problem to problem. All right, and then what you want to do is break it down. So when I say break it down, I mean, like, we know 25 is a factor of 50, so it's going to be the square root of 25. And then what do we multiply 25 by to get 50? 2. All right, and then what about that 5? How did we get 5? Very good. So then the last step is to take the square root of the perfect square. And then the number that's not a perfect square doesn't change. It stays underneath that radical. And the number that is the perfect square comes out, and it changes to what the square root of 25 is. All right, so the second one, I don't have any room for steps because you can go straight from the problem to the answer. So how did I end up with 4? You added 1 and 3. So you have 1 square root of 2, and you add 3 square roots of 2 to it, and it gives you 4 square roots of 2. So in the steps, what I want you guys to write is that you can only add and subtract like radicals. And then when you're adding or subtracting, you add, I'm going to call them coefficients, but I'm putting it in quotes. A coefficient is really the number in front of a variable. A radical is not a variable. So it's not technically a coefficient, but if I say it's call it a coefficient, you'll know what I'm talking about. Okay, so next we have the square root of 32 minus the square root of 2. They're not like radicals, so we can't subtract them and get the square root of 30. What are we going to have to do? Okay.
Perfect square of the 32, which there is 1.
Is it? There is one. Yeah. 32 actually has 2 squares that go into it, 34 and 16. Now, we always, if there's more than one, we always want to use the larger. So let's just start off by simplifying the square root of 32. Let me spell it right. Okay, so someone says 16, so 32 is 16 times 2. All right, and then I just brought down the other minus square root of 2, and then we want to go ahead and take the square root of 16, which is just 4, and then everything else stays exactly like it looks. And then when you subtract what's kind of like a coefficient, you get 3. Square root of 2. All right, I think this next one was the easiest one out of all of your cards. So we're multiplying. They're both underneath the square root, so you just multiply. So if the numbers are under the square root before, when you multiply them, they're still under the square root. All right, now it takes us to all the fractions. So on your orange cards, you had fractions with a radical in the denominator. So I'm going to show you something. You do not have to write this down. So I want to show you why it's not simplified if you have a radical in the denominator. And you have to go way back to when there were no calculators, like back before I was alive, because there's always been calculators, I think, since I've been alive. But there used to be people who had derived the square root of numbers, which you can do. I don't remember how to do it, but you can do it. And then they put them in a book. And so when someone needed to know what the square root of 2 was, they would look it up in a chart. And so if you had 1 divided by the square root of 2, which is what we basically have, they would look in the chart and see the square root of 2 is about 1.414. Now, do you guys remember how to divide by a decimal? It's a mess. I see people doing it. Yeah, so we would have to move this decimal over 3 places and then move that decimal over 3 places. And now you're dividing by a 4-digit number, which is no fun. So they figured out that you could rewrite this in a way that you're doing the square root of 2 divided by 2. So that's 1.414 divided by 2. That is not hard. You just bring the decimal up. 14 divided by 2 is 7. And then 14 divided by 2 again is 7. So you can do that super fast. So that is the reason, back, I don't know, a long time ago, that they decided that you cannot leave a radical in the denominator. Doesn't feel as relevant right now because we all have calculators that can do square roots, but that is the reason. But we're still doing it. So the first thing I want you to write is that you cannot leave a radical in the denominator. All right, and I'm going to show you, I think that if you remembered this, you probably kind of remembered a trick that works. I'm going to show you what you're actually doing mathematically, but if you can just look at it and tell the answer, you don't have to show all the steps. But what you are technically doing is you multiply the numerator and denominator by a radical that will make the denominator a perfect square. And a whole lot of the time, it is just whatever that denominator is. It doesn't have to be, but a lot of the time it is. So in this case, if I want to make the denominator be a perfect square, what I would do is I would multiply it by the square root of 2, because 2 times 2 is 4. That is a perfect square. Now, to keep it legal mathematically, we also have to do that on the numerator, because this is like multiplying by 1. And multiplying by 1 doesn't change the value, it just changes what it looks like. So what would I get on the numerator if I multiplied 1 times the square root of 2? Square root of 2. And the denominator? Good. And what is the square root of 4? Just 2. Now, it's going to be awesome for me eventually, or maybe even now, if you guys notice that the square root of 2 times the square root of 2 is just regular 2. If you have the square root of 5 times the square root of 5, it's just regular 5. Always that works. Or you can show every step. I will never tell you you're showing too many steps, I promise. Okay, the next one is almost identical. So same thing, we're multiplying by the square root of 2. Can I multiply 3 times the square root of 2 and get the square root of 6? No. The 3 is outside, it has to stay outside. And then 2 is inside, it has to stay inside. And then same thing, we get the square root of 4 on the bottom, which just is regular 2. Okay. What do we do on this one? We just divide it. So if both numbers are underneath the square root and they divide evenly, go ahead and divide. Now this next one, they don't divide evenly. Like you wouldn't want to say that this is the square root of 1.5 because that is like a decimal inside of a square root or a decimal inside of a fraction is never simplified. So we're going to go back and do what we did a second ago where we're just multiply by the square root of 2 in the numerator and the denominator. This time, because they're both under a square root, I can multiply those and get the square root of 6 over the square root of 4, or just the square root of 6 over 2. Alright, so that was the cards. And that was a lot for you guys to remember. I just wanted you to start thinking about it and seeing what you could remember, or just kind of like use logic to put them together and then go back and talk about the steps. Alright, there are a few that we didn't cover in the cards. I just want to do a few more examples with you, and then you can work on your assignment. Now, to me, to do these simplifying radicals problem is extremely helpful to have a list of perfect squares and a list of perfect cubes. Now, obviously, there is an infinite number of perfect squares and cubes, so we cannot list them all. But we can start with just like 1 through 13 squared. We'll do that real quick. And then you probably have less cubes memorized. I don't know. It's good to have some memorized. If you don't have it memorized, like I could take what 2 squared is and multiply it by another 2, and it's going to give me 2 cubed. And same thing, 9 is 3 squared, multiply it by another 3, we have 27. So it gets a little more difficult when you start having more digits. But I think we're good. If you just go through 6 cubed, that's probably good. And then the same thing with perfect squares. You have 2 options. You can take the perfect 4. You can take a perfect square and square it. So 1 squared is 1, 4 squared is 16. Or you can take a perfect cube and multiply it by another 2 or another 3. So either way, I want you guys to start doing more things in your head and relying less on calculators to do things. Okay, So for example 1, we have a fourth root, which we haven't done yet. So we have this list right here, perfect fours. My daughter is about to take the GRE, and so she took AP Statistics as a senior in high school and passed the test and hasn't taken a math class since. And so there's a whole math portion on the GRE, and so she's reviewing things and she's learning like shortcuts and tricks. And one thing that came up when I was helping her is like if you're like wanting to find one of these perfect fours that goes into 243, only odd numbers are going to divide evenly into an odd number. So if it's an odd number, there is no even number that divides evenly into it. So don't even think about looking at 16. Now, 256 is too big anyway. But the only one in this list that even possibly could work, besides 1, is 81. Now, even numbers don't work that way. So odd and even numbers can divide into even numbers, but only odd numbers divide evenly into odd numbers. So that's one thing that can save you some time. Does 81 go into 243? Yes, 3 times. Good job. So we can break that down to the fourth root of 81 times the fourth root of 3. And then how many times, what is the fourth root of 81? 3. So it's just regular 3. And then we just multiply 5, 3. And then the other, I put too many 3's in this problem, sorry. The other 3 stays underneath the fourth root. All right, okay? All right, 2 isn't like a hard problem, but we didn't have any quite like this in the card sort. So just instinctively, what do you think we would do? We're definitely multiplying. What do y'all think? I think you know, you just don't want to tell me. So the numbers on the outside, we're going to multiply to get to multiply by each other, and it's going to go on the outside. And then same thing, the numbers on the inside of the radical, we're going to multiply, and it's going to go inside the radical. Are we done? What's the square root of 16? 4. So this is just 32. Okay, and one more with a cube root. So we have the cube root of a negative. Can you do that? It's the square root of a negative that's imaginary. So what if you took negative 2 and you multiplied it by negative 2 and then multiplied that by negative 2 again? What would you get? Negative. 3 negatives make a negative when you're multiplying. So negative 2 times negative 2 is positive 4. Positive 4 times negative 2 is negative 8. So it's perfectly fine to have the cube root of a negative. That is fine. So let's just leave that 2 out, and we're going to break down negative 40. And I'm just going to go ahead and make my perfect square be the one that's negative. I'm sorry, my perfect cube. So what perfect cube goes evenly into 40? 8. So 40 is 8 times 5. So negative 40 is negative 8 times 5. And then what's the cube root of negative 8? Negative 2. So we get negative 4 cube root of 5. All right, so the assignment for this lesson is just right underneath the notes.